What's up, guys? It's me again, Sir Ernest, and today we're going to talk about magnetization and magnetic susceptibility. The problem reads, a coaxial cable consists of two very long cylindrical tubes separated by a linear insulating material of magnetic susceptibility Chi-M. A current I flows down the inner conductor and returns along the outer one. In each case, the current distributes itself uniformly over the surface, as in this figure. Find the magnetic field in the region between the tubes. Okay, so here we're going to, because we're given with the magnetic susceptibility, so we can calculate the magnetic field by knowing first the vector H. And then from vector H, we will use the relationship between the magnetic field, B, your susceptibility Chi-M, and your vector H by this equation. Okay, so first let's compute for H, and we're going to use Amperes Law. Okay, so we're going to look into the magnetic field between the tubes, so within this region. And in order to do that, we can use this Amperean loop that encloses the inner tube, where the Amperean loop is of circle, and the distance from this point or along this point will be S away from the center of your coaxial cable. Okay, so by Amperes law, we now have integral of H dot dl. Okay, by symmetry, because the Amperean loop is a circle, so our dl would be the circumference of the circle. So this is now equal to H times 2 pi s. And this is equal to I enclosed, where your enclosed current should be the free current that is enclosed by this Amperean loop. Okay, which is equal to I. So therefore, your auxiliary field H would be equal to I over 2 pi s, and then the direction will be p hat. Okay, so this is the direction of your p hat. Now by definition, therefore, B is now equal to mu naught 1 plus Chi-M times H, which is I over 2 pi s p hat. This is now your magnetic field. Now let's see if this is correct. Now as a check, okay, what we're going to do is we're going to do a similar calculation, but this time we're going to calculate first the magnetization and the bound currents. Then we'll see whether this will produce the same current at the same magnetic field. Okay. So the magnetization is defined as what? That's the Chi-M H. Okay, so magnetization is equal to Chi-M H. So therefore, this is now equal to Chi-M I over 2 pi s times p hat. Okay, from here, so from here we can calculate the bound currents. JB would be equal to the curl of M. This is equal to, because remember that M is a function of S, and that's along the phi direction. So the curl part, so the only component of the curl that will survive the cancellation would be 1 over S times the derivative with respect to S of S times M along the phi direction, which is chi M I over 2 pi S Z hat. As you will notice that S will cancel. So what remains in this, inside the parenthesis, is a constant. So the derivative with respect to S of a constant is 0. So in short, there will be no bound currents within the volume. For the surface, KB would be magnetization, and take the cross product of that with the N hat. In this case, our N hat would be S hat. Okay, so this becomes chi Mi over 2 pi S P hat cross S hat. Okay, and this is now equal to two things. One here, and one for B and one for A. So this is now of two values, chi M I over 2 pi A Z hats, and negative chi M I over 2 pi B Z hats. The negative sign here tells you that the direction of N hat would be negative S. The direction here would be positive. Okay, so now the total enclosed charge will now be equal to what? This is equal to the current here that is enclosing this particle plus chi M I over 2 pi A times the circumference of this circle, so that's 2 pi S, and this is equal to 2 pi will cancel, so the total enclosed would be S would be equal to A, so this will also be cancelled. So this is 1 plus chi M times I. Okay, so this is the total charging current enclosed. So by Amperes Law, B dot TL would be equal to B times, again like this one, 2 pi S, and this is equal to mu naught I enclosed, which is equal to mu naught I plus chi M I. So again, this one is for R equal to B, so this is S is equal to A. So whether this is A or S, it's the same thing here. So again, going back here, we now have B will now be equal to what? B will now be equal to, correct, this is mu naught 1 plus chi M I over 2 pi S, and we know that this is along the phi direction, and this is your magnetic field. And let's go back here. So yes, that's the same. Okay, amazing, right? So that's it. This is the solution to problem 6.16 of your book. I hope you learned something today, and I'll see you guys in the next video. Bye-bye.